Morning. All right, good morning. Morning, how's everybody doing this morning? Good. All right, so slight change in the schedule. As you saw, there's no RLC assessments that are posted, nor is there an RLC quiz for this week. So I am just going to cancel this week and then plan on next Monday, the 2 assessments with the quiz on the Tuesday. So the change is that we will not have these 2 assessments and this quiz. Instead, we'll just wait and do the assessments next Monday and then the quiz on Tuesday. All right, is that clear? Okay, you'll still have, and there was a discussion, it looked like it was very active yesterday, so good job on that. I have posted those going forward, so you can start to comment on those before the actual Monday. So you can start on assignment number 4 for that discussion. And then some of you did see that there's an exam 1 group that's going to be a preparation for the first exam. So it's you already are put in a group, but if you guys want to work with the groups that you work on, together in here, feel free to move yourselves around. I left a couple empty ones that people can move as a full group if you want to. If I see that there's a minimum of 3 people, so if there does have changes so that there's a group with less than 3, I may move you manually to another group if you're not in one that's at least a group of 3. With that, there's a little bit of information on, sorry, wrong one. Let's see. Discussions. All right, so this group 1, it has a little video that will go through how you actually do this, but in the side, there's this groups tab right there. And for your group, there'll be its own web page. So you can actually go and do discussions there amongst your group, communicate, post files that way if you want. And then when you have completed the whole assignment and collaborated to get the 3, at least minimum of 3 problems. So the number of problems depend on the number in your group. So if you have a group of 5, you should have 5 problems. Unless somebody didn't participate, then there'd be a group, 4 problems. But once they're all compiled, then upload them here for this this exam 1 group assignment. So do make sure that you transfer them over from your group webpage to the discussion on this one so everybody can see those. So those should be extra problems to help also go through, and you can use those as a preparation for the first exam. Yes?
So each person in the group works through a problem.
Yep. Yeah. So that's the goal, is that you do at least 1 problem. So I would encourage you to try to do the problem that you're not as familiar with to help prepare for the exam. The goal is to use this as a learning experience to prepare yourself better for the exam. So that is the goal of this. And typically doing it together, you can, so what you're supposed to do is create your own problem, create your own solution for 1 problem, and then let the group look through it and they solve it to see if they get the same answer. If they don't, then you have a discussion of, well, what did I do wrong? And so that's where that learning experience comes in. Does that make sense? Okay. So that is also coming up. So if you want to get started on that now, you'll be able to do, all 3 of these types of problems. So the exam will cover RC circuits, RL circuits, and RLC circuits. So you'll most likely have 3 or 4 problems. One of them may be more of like a little bit of an understanding problem that we'll go over after we go over a few more of the examples for RLC. And then you'll have an RC circuit and an RL circuit. So hopefully the content of it is straightforward. It's just making sure you know how to do those problems and feel comfortable with that. All right. Any questions about what is expected for the content? So a question came up on the group or on the chat. If you want to move groups, you're welcome to move groups. And so if you go down to people and you go to the exam 1 group work, on your tab, it will be a little bit different. It will have leave group or join group. And so over on the right side, it should say leave or join. And so if, again, you guys want to even discuss in your groups that you work on in here, you can see at the bottom, there's 2 groups that are 0 out of 6 students. So if you want to move as a full group, you can move. And then that would leave other groups to have less numbers. If you're fine with the group that you were already assigned to, feel free to stay in that group, but this way, if you do want to move, you're welcome to move. And so for yours as students, you'll have a different view here. But again, it's under the people tab on the left, and then there'll be that everyone, but then there's an exam one group work. So you can have that one. And that would be a leave or join tab. All right, any other questions? Okay, so that is what is coming up. Again, there will be no assessments or quizzes this week, and we're going to just continue to work on these RLC examples and hopefully start feeling more and more comfortable with them. So last time we went through the RLC, a new example. This was problem 6.24. I just want to briefly go through and review what are kind of the steps now for these RLC circuits that are slightly different than the RC and the RL. So anyone want to say, like, where would I start if I'm trying to solve an RLC circuit? Correct. So identify first. Oops, there we go. Series or parallel configuration. And what time frame do you look at that one? Because that can vary if you look at it at the initial time or the final time. Which one? Correct, final. So look at the final time to see what configuration it's in. So that can make a difference on if it's series or parallel. Okay, second step. Okay, so calculate alpha and omega. And again, this may vary if you look at it at different timeframes. So what time frame do you want to use in this one? Okay. What time frame would you look at it in this one?
Final.
Correct, the final again. The final over here. All right. So once you calculate them, then you need to do what?
Determine if it's over damped, critically damped, or under damped.
Correct. So determine overdamped. Critically damped. And underdamped or underdamped. And what determines that? Correct. So I'm going to just do a screenshot of that. So either alpha is greater than omega naught or equal or greater than. So you compare the two to determine which one it is, and then look at that. Omega naught. All right, and then what? After you've determined overdamped, critically damped, underdamped, you know also if it's series or parallel. What are you going to do next? So if you know if it's overdamped, critically damped, or underdamped, you know what? What does that tell you?
General solution.
Correct. You can look at that and say, okay, then I know the general solution form that it needs to be. So this helps to identify what is my so that helps you to identify that what will be the general form solution. So what else do we need to know to write that form? I'll go back up here. Okay, so say it's overdamped, then I know that it's gonna be of this form, right? If it's, which one's a series? So I know it's series or parallel. We already identified that. And then I identify overdamped, critically damped, or underdamped. So then I know general form solution from this table, but I don't know every information here, right? So what else do I need to know from here?
Initial values and final values.
Okay, so
Current voltage.
yep, so it will be dependent on which one. Some of them you need to know the roots, which are S1 and S2. Some you need to know VC of 0, VC of infinite, IC of 0. So there's different variables in there that you're going to have to determine from the initial circuit and the final circuit. Did you have a question or comment? Sorry, I didn't. Okay, all right, thanks. Yeah, so depending on which one it is, all of them typically need initial values for your current or voltage, or both, and then the final value for voltage and current, depending on which one's series or parallel. So one other critical thing that you have to understand is that if we're in series, we're finding one variable, which is VC. And if we're in parallel, we're finding IL. From there, you're going to use that to determine any other variable in the circuit. Okay, so the next step would be, where do we go? So if we're in the series, we're finding VC. So we're going to find the initial value for VC, the final value for VC, and then usually the current I. For some of them, you need to find that current. And then for others, you need to find the roots, S1 and S2. So depending on which one it is, we're going to find final values, initial values, and possibly roots. And the roots are the S1, S2. So those a root, if you remember what is a root to a system? You have a system of equations and you find the root. What does that mean?
When everything's zero.
Okay, so that's a solution to the system of equations. So that means it's a solution. So S1 is called a root, is a solution to those sets of equations. So S1 would be a solution and S2 would be solutions to those sets of equations. Alpha and omega are going to be variables that help you understand the characteristics of how it's moving. So we know final and end values for these, and then we're trying to understand how does this move from that final to end value. Does it move as a critically damped or underdamped, or which one did I miss? Overdamped. So how does that move? Does it oscillate a lot or does it oscillate a little bit? And so those values of alpha and omega naught help you understand how that is moving from one final value to from the initial value to the final value and what form that takes. So does it have a lot of ringing or not? If you have a higher or lower value of alpha and omega naught, that's what's happening. So, all right, so now we know final values, initial values. So these are all the variables that were unknown for the general solution. So from here, once we know all those, what do we do?
plug them in.
Correct. Just plug them into the general form equation. Plug into general form equation. And then you're done. That's the end goal. All right, so this is my own methodology of solving these kinds of circuits. So rewrite this, I suggest you write it in your own form. One last thing, once you plug it into the general form is if so once you get that equation, if you want to know a different voltage or current through a different element in that circuit, you use that voltage or current. Depending on if it's series, you're going to use the voltage across the capacitor equation. And if it's an inductor, you're going to use that IL current equation. So you would use that as a known value and then write either a voltage loop equation, whatever the voltage, whatever you need to put the other variable you're trying to find in terms of that voltage across the capacitor or current across the inductor. Does that make sense? Yes.
Do that by just taking the derivative of it.
So it depends, like if you want to find, let's see. All right, so say, for example, you want to find this current here. Then you know the 4 milliamps, and then if you have a description of the voltage across the capacitor. So for this one, let's see, open it up, it's going to be series. Yes, so this would be a series, and then you would have VC. So if I know VC, then I can find IC by the relationship of IC, wait, no, B, dV, C dV dt is equal to IC. So I can get the current through that capacitor by taking the differentiation of it. And then I can do a current summation. So I'll have a constant plus that IC, which will be some exponential form. Okay, that makes sense? So yes, that would be how you would use that. So depending on what you're trying to solve, if I wanted, see if I have voltage, there's going to be no current. Yeah. Just trying to think if you wanted the voltage across that resistor instead, you would still have to find that current, this new current I, and then you would take that I times 0.1 to get that voltage across that resistor. And then Vx would be I times 0.1. So you would use, these for different ways to find different variables in there for current and voltage. All right, other questions? Any questions? Okay, ready to try some more? So we're going to finish the problem that we were working on last time. So last time we identified it was a series RLC. And then we found alpha and omega naught in the final position. Then we compared alpha and omega naught, and it was overdamped. So we used the general form solution for the overdamped. And we saw we needed IC of 0, BC of 0, BC of infinite, and S1 and S2. So we had to find all those variables. And I think that's where we ended. So let's continue on to find those variables. So S1 and S2 we found from alpha and omega naught from the equation. So again, there's an equation for that. And remember that comes from that second order differential equation solution is where that was derived from. So then we looked at the initial value to get VC of 0, which was 0.2 millivolts, and IC of 0, which ended up being 2 milli. So we have S1, S2, IC 0, VC of 0. And so we now just need the VC infinite. So at the final stage, we need VC of 0. VC of infinite. So final stage, T equals 0 means that the switch became an open. So this was our original circuit. So this becomes an open. Sitting for a long time, what does the inductor do? It become a wire, and the capacitor becomes open, correct? So this one will stay open, this one becomes a wire, and then this becomes open. And VC was labeled as plus to minus stopping. So what is going to be VC here? It will be what? So, yeah. Correct. So 0.4, sorry, 4 milli times 0.1 or 400 microvolts or 0.4 millivolts, whichever one you want to write. And so that will be our final value. So now we have all the variables. And so we're just going to go and plug them in. So we're going to find A1 first. A1 is an IC. IC was given as 1 over 1.8. And IC of 0 was 2 milli. S2 was minus 7.76. And VC of 0 was 0.2 milli. And this was 0.4 milli. And S1 was a minus 4.64 minus a minus 7.76. So this was 6.24. And then A2 is 1 over 1.8, IC of 0, S1, which is the minus, so S2 is a minus this, so this will become a plus, 4.64. Okay, maybe not. Oops. Not gonna let me do it smaller. All right, guess not. VC of 0, which was 0.2 milli, 0.4 milli all over S2, which is minus 7.76 minus 4.64. And then we can plug that into VC of T. I'm gonna look this up. I did this. All right, 0.66 millivolts. I'm gonna copy these. So A1 here ends up being a 0.66 millivolts. And A2, oh, wait. No, that is right. 6, 2 milli, 4, okay, minus 0.86 millivolts. For VC of T is equal to 0.4 plus 0.66 e to the minus 4.64 t minus 0.86 e to the minus 7.76 t. So this is only valid. You can say it's greater than T0 because that's when the switch is flipped. Or remember, you can write this as U of T. So either way is correct way of writing that. No, U of T milli, so millivolts. Yeah. So instead of writing T is greater than 0, remember U of T is just, it's a 1 when it's greater than 0 and 0 when it's less. So you can just write that in that form. Just understand that that's what that form means if you see it. I think it's more descriptive to just put T greater than 0 to understand that. So whichever one you're comfortable, but you are going to see that U of T sometimes. So you just need to understand what that U of T means.
So it has to be greater than 0, not greater than 0.
So right as it switches, it's a good question. It's undefined right as it switches because it's like either right before it or right after it. So it's really hard to define it right at it.
Okay.
Does that make sense?
Okay, so it's only defined after.
Yeah.
uh,
After
it
0,
shows.
correct.
Okay.
Did you have a question or were you just going to comment on that?
Say 0, distinction doesn't matter because everything takes time to happen. So it's-
Correct, yes. So that's the issue, is that because this doesn't have an initial response because it takes time for it to change. So we're talking about realistic things. Ideally, yes, you could define it there, but it really won't happen because nothing happens instantaneously with capacitors or inductors. So yes, greater than 0. All right, other questions, comments? Okay. I'm gonna
Is
put,
the step equation defined for greater than or equal to 0?
good question. No, yeah, it's greater than or less than. It's not defined at it.
Ah, okay.
Yeah.
So, yeah, it has no definition.
It has no definition at 0. For that reason, we're talking about a more realistic situation. Okay. All right, I was going to copy this. Let's see. All right, so this is just written out in a nicer form. So I'm going to just put it on here too for your notes. All right, so there's A1, A2, and then the expression for VC of T. But we actually wanted the IC of T. And so, as I said, once you find the VC of T, then you can use that to find another variable in there. So how will we find IC of T here? We have VC of T. So capacitors, the description though is different. You can't just use Ohm's law for that one.
So with a capacitor, we have current equals capacitance times the derivative of the voltage function.
Correct. So we would take the differentiation of VC, multiply it by C, and that will get us that. So I like that idea. Like, yes, it would be nice. It reacts the same way as a resistor, but unfortunately it doesn't. So we have to use the relationship between IC and VC. Does that make sense? Okay. All right. All right. So taking the differentiation of this, the 0.4 goes to 0. If you guys remember the differentiation of an exponent, what happens? Okay, if we don't have a T in the beginning, then we just take this variable that's in front of the T for the exponent and bring it down and multiply it by the first number. So it'd be 0.66 times a minus 4.64 E, and then it just stays the same. And then the same thing for this one, we would have 0.86 times a minus 7.76 e to the minus 7.76 t. And so then multiply it by C and you end up with this equation. And now since IC can change instantaneously, but the voltage can't change instantaneously. So this one can be greater than or equal to 0. If you don't really remember, is it equal or greater? It really doesn't matter, right? Like, do we care exactly what it is at 0? It's not really going to matter. So.
In this case, would we not use U of T because it's also equal to 0?
Correct. Yeah, so for any other variable in the circuit, except for, well, I shouldn't say every, this has an inductor in the circuit. So across the inductor, the current across the inductor can't change instantaneously. The voltage can, but the inductance or the current cannot. Capacitor, the voltage cannot change instantaneously, but the current going into it can. So the outside of the capacitor, the current can change right outside it instantaneously, but the voltage across it can't change instantaneously. That makes sense. But that may be very confusing, and so it doesn't really matter. Yes.
Should that be greater than 0?
It can be greater than or equal.
I thought the other one had to be greater.
So that's what I'm saying. It's confusing. So don't worry about it for now.
Okay,
It's good. I'm gonna count and correct whether you say greater or equal right now. It doesn't really matter. Because when you go and build this realistically, you're not gonna be able to time it right at 0 anyway. So that's why I say it doesn't really matter. Yes, Taylor.
How much you find the current over the inductor? Is that just finding like the voltage difference between that node, the two nodes in between the inductor, and then just kind of using Ohm's law?
So his question is, okay, what if I don't want IC here, but I want the inductance here? Or I mean, I want the IL. What do I notice? In the final circuit, this is going to be the same. So you would just say IL would be I equal to IC there. So that would be how you would find that. And then again, if you wanted to find the current through this branch instead, you would take a current summation. I'll call that I1. And I1 will be so you would do a current summation there of -4 milli goes in, I1 goes out, and IL goes out, or IC. So IL is going to equal IC. And so I1 here is going to be 4 milli plus IC. So you would just write that IC equation below. And that would be your answer for I1. Did you have another question, Taylor?
Yeah, I'm just wondering, is this why when it's like it's important to figure out the series or parallel, and then in the series you're finding B of C since it's in series, that kind of determines the current of the inductor versus if it's parallel, you're looking for IL. So that's kind of an easier way of figuring out the voltage across the capacitor.
Yeah, so if you're in parallel, yeah, you do have to find the IL instead. And then you could use that because you are in parallel with it to find.
I guess what I'm asking is like, when they're in series, is the capacitor determinative of what's going on in the inductor, and then they're parallel, the inductor is determinative of what's going on across the capacitor?
Yeah.
Okay.
That could be one way you could view it, yes. 4 mil what? Yes. Thank you. Yeah, sorry about that. Minus IC. Okay, I have a couple questions online. Let's see. So yes, so online they also asked if it was always in parallel, would we expect to be finding the current through the inductor? Correct. So you'd find the IL instead. Did I write something wrong? For C, it would be 1 over 1 point. I mean, sorry, here this would be 1 over 1.8 for the value of C. And if it's 1 over C, it would be, yeah, you're right. I miswrote this here. This is 1 over 1.8. Thanks for catching that. And that's 1 over 1.8. So it'd be 1.8 there. So 1 over C would be 1.8. Sorry about that. Thanks for catching that. Yes. Thank you. Yes. Also, the person online did catch that that was a minus IC. There was one other comment there. Okay, so the other question was if you have a plus and a minus. So I could actually have this backwards and a plus to a minus this way. So I just was told that that was the plus and minus. So if you guys been in labs, some of the capacitors have a plus and a minus, so they're actually polarized. some are not. So then you can define if they're not polarized, which direction there actually is the plus and the minus. But that does not, one of the questions online was, does that determine if it's in series or parallel depending on the plus and the minus? Actually, it does not, right? It's the form of what location the capacitor and the inductor in it to determine if it's in series or parallel. So polarity does not determine whether I'm in series or parallel form. Hopefully that answers your question, Sam. All right, any other questions about this? You guys ready to tackle another one? Yes, question first.
So are the A's or the always gonna be the same?
Yeah, they were, I just miswrote it, but they don't change. All right, so this is going to be, is this the one we just did? I think this is the one we just did, right? Yeah, 6.24. Okay, so you guys are gonna do 6.26. So go ahead and break up into small groups and first determine what?
Series or RLC?
Correct, series.
Series or parallel?
Series or parallel. After you identify if it's series or parallel, then what are you gonna do? Correct. Calculate alpha and omega naught, and then what? Correct. Use those values to determine critically damped, underdamped, or overdamped. Then what? Once you identify series, parallel, alpha, omega naught, critically damped, underdamped, overdamped, then what do you do? Correct. Find the either initial and final, and if you need S1, S2. Do what? And then you plug them in, correct. Okay, so go ahead and break up into your small groups to work on proceeding through this. All right, for you guys, I'm gonna move you guys to a breakout room just so you can talk and not be on our overhead microphone. Okay, so finding if it's in series or parallel, you have to put it first in the final form. So here you see, yes, it's in series once I draw that final form, where that means where the switch is in the final position. So series.
Can you
Then the
share your
next step
screen?
is to determine alpha and omega naught. And so one thing to recognize, if you're in series, your RTH is going to
Professor
be
Rasmussen, can you share your
outputs.
screen?
If you're in parallel, that A and B will be across the inductor, and that can make a difference for your alpha and omega naught. So the inductor is the driving force for a parallel form, capacitor for the series form. Okay, so that's another thing to note. Otherwise, you could get a different answer for alpha and omega naught. So for series, make sure that alpha or the RTH and for parallel, that RTH
Professor
is from
Rasmussen,
the,
can you share your screen?
and
Professor
when I say
Rasmussen,
C, that's where you're gonna put the A and B value. And then find the,
Professor Rasmussen, can you share your screen?
and so then you're gonna take a pathway here from A to B of the capacitor. And so that shows that this becomes a wire. And so your RTH here is just going to be R1. So you have R1 over 2L, which gives you 2.5 meters per second. And then omega naught is just the 1 over square root of LC. So you should find the 2.45 radians per second. So this does show that alpha is greater than omega naught. And so you are overdamped. Copy that one. So now we need to find the variables.
Professor
And
Rasmussen,
so S1 and S2 are the alpha plus or minus alpha plus or minus the square root of alpha squared minus omega naught squared. And you get -2 meters and -3 meters per second for S1 and S2. And then we know the general form, and we need A1 and A2. So redraw the circuit.
Professor Rasmussen, can you share the screen, please?
So at infinity, so in the final state, you're going to have the capacitor is open, the inductor is a wire, and then your the switch is open. And so VC is just going to be VS, which is 24 volts. And then in the initial state, should have done these backwards. In the initial state, you're going to do 0 minus, and you're going to find in 0 minus that VC of 0 minus is 16 volts, and then the IL is 4 amps. And then remember that the current through that capacitor can change instantaneously. So you have to find it at 0 plus. So you have to do the one extra step. So at 0 plus, you're going to use the IL minus that you find and then the VC minus that you find. So you use the current source and the voltage source. And then this gives you a value of IC of 0 will be that 4 amps. Okay, yes.
How could zero minus to make the zero, how could that change? Like, I don't understand the point of putting them in as a voltage source or current sources. Like, how would that affect like IC or DC as well? Does that make sense?
Yeah, so for a capacitor, the voltage across it can't change instantaneously because your, let's see, IC of C. How do I describe this? No, that's not a good way to say it. So the charge across the capacitor, you have the 2 plates. And due to the physics of it, they cannot change instantaneously as far as the charge across them, right? Because they built up charge or they discharge. And so it takes some time for them to build up that charge or discharge. So when you think about like, okay, but I can force current into it and I can force current into it, but the charge on it is not, or not the charge, I should say. The charge can change, but the voltage takes time to accumulate. So hopefully that makes sense. So inductor's harder to visualize, like you can visualize that, like, okay, I can visualize the charge coming up on it. And I can, visualize that charge going off on it. Inductor's a little bit harder because the current in it is what cannot change instantaneously. So for capacitors, voltage cannot change instantaneously. But the current can, and then it's opposite for an inductor. The inductor current can't change. Instantaneously, but the voltage can. So because the voltage can change across that inductor and then the current can change, we have to find it right after the switch because it will be different values right before and right after. Because right before you can see there's no current, IC is 0. But then because of the external connection, that current it has the ability to change instantaneously. Does that help?
Yes.
Okay, all right, yeah. I know it's kind of hard to like, how do you visually understand this? All right, I'll post the end solutions for this one so you guys can compare the rest of the solution to it. And we'll see you guys on Monday. Oh, sorry. Here, I'm going to share my screen. I'm so sorry. Yes. They're like, I forgot to share my screen. They're like, please share. Sorry, guys. All right, questions?
I want to know how you got to that value because I did this like again, but I keep getting my own like 0.002, and like from like based on the assessments, I thought that was gonna be correct. But then
So is this, which one is this one?
this one is the quiz.
Quiz, okay. That's the capacitor, right? That is wrong. Yeah, I had an error in mine. So let me see.
Error in my answer.
No, in mine. So it could be right. So he's gonna go in manually and grade all these for the capacitors because I had an error in my solution.
Okay.
Automatic one.
Okay, yeah, because I was like so confused. I was
We
like,
did
how
something
is
wrong.
this?
Something wrong.
It
They
could be
won't.
right.
They won't.
So, yeah,
Okay.
You could be right and my answer.
Yeah, because like when I switches,
Let
that
me
means it's like
see.
considered open out like that. Well, those wording confused me. So
I was very confused.
I was like, what does that mean?
I thought I had it right to answer. I'm gonna have to go back and fix that.
Sorry, guys. There we go. Yeah.
Yeah. Did you get it somewhere?
Not the same, but different values, so
Professor,
it could be different.
so when it comes to the current, like these initial values in the equations, are we using the t at 0 minus or 0 positive?
So
Or
you,
how should I
they're
think of
always
that?
at 0 plus for any initial value.
Mhm.
But for the capacitance, since it doesn't change, if you find the 0 minus, it will be 0 plus. IL will be 0 minus and then 0 plus.
Okay,
So
and that's-
initials always at 0 plus.
0 plus.
Yep.
But it's if, okay, but it'll be equal if it's voltage of a capacitor or current. of an inductor.
Yep.
Got it.
Correct.
Okay, so.
Sorry, let me, I have the solution on here. I was just trying to find it. Let's see.
Value plus 002 sounds right to me.
So what did you have for,
0.00.
you had 56,000 and 4 nano. Yeah. Maybe not. I was gonna say mine is, I have different values.
But even with different values, it should still be like all either negative or positive.
Let me see what I,
I was just like based on like the homework problems or like 0.0019.
I think,
like,
and I don't know.
When I looked
if-
at that, I was like, that looked really correct.
I-
That's like, oh,
Yeah, I mean, I got it wrong too, so I don't know if I did it right or wrong
I don't know.
versus mine too. So.
let me see which one is close to it. You got 50. These are the correct values. So you had around this. From like minus
No, not even close.
1.7.
56, 204.
Minus 1 point something.
I had 0.002, so I was even close. I'm just a little bit confused on how to approach the problem.
The part where I was confused about the quiz question
Yeah.
is in when the switch is at position one, how the voltage source and the current source would interact with each other over the capacitor. Or if they even would, because like the capacitor is considered open.
So
I think that's where I messed up. I don't know if that.
like I had the idea where the current would just like if it like passed through because it passes through the least amount of resistance.
Yeah.
So it just goes literally straight through.
So when you're in the final position, even though this is open, you're gonna have a voltage here on this side, like a VX. And so this is gonna be a difference. So it's like, if I take my multimeter, I'm probing it. I'm gonna probe it at the VX, and then I'm also gonna probe it right here,
Yeah.
which is also gonna be 1 volt. So it would be the difference between VX and 1 volt. Between those two spots.
That makes sense to me.
Okay.
VX,
I don't know if
like
that's-
so like VX right up here.
Uh-huh.
Why would you give? Oh, is it just because it's like a supernode or like a node?
Well, this is, there's no current flowing in these branches, but
Yeah.
here,
Yeah,
all this
okay.
current goes through here. So 2 milli times, whatever that R1 is.
So
gonna be
it
your
would just be like
VX.
VX. So negative. So it goes this way, right? So it's just be, or would it be going this way?
So this is an open. So the plus side of it would be like if I have a multimeter and I take my positive red wire, I measure it there at the VX value, and then I measure here right above the 1 volt.
So yeah, so the direction would go there and be up negative, and then you change it to VX -1. That would make sense.
Yep. And so your question was when what?
Like I was just wondering like why I like how I got like a completely different value. That's all. I was just like.
Yeah, so
completely off.
initial time, I'm gonna probably come in here. Let me,
I can just go to later. I can come in later again and just do work on it later.
okay,
Like once it all corrected again, because if they ask for an issue and then I still get it wrong, I'll just come back later.
okay, sounds
Just
good.
make it a little easier. So. I don't panic.
And then I have a different question real quick too. This is just a conceptual question because I always get confused on this. So for initial, for the amperage on this one,